So we're going to start here talking about really bonding in this chapter. I know it says covalent bonding. We're going to talk about ionic bonding and covalent bonding. And really this chapter and the next chapter really sort of intertwine with each other. In this chapter, we talk about really drawing all the structures and all those things. And then next chapter, we talk about everybody's favorite stuff, geometry and some new stuff, hybridization and polarity, molecular polarity, and all that kind of stuff in sort of the next chapter. So they really go together, the two chapters. So we'll start here, obviously, with the basics. So when we represent bonding, be it ionic bonding or covalent bonding, we oftentimes will use Lewis dot symbols to help us do that. Lewis dot symbols are also sometimes referred to as just simply electron dot symbols. They're basically the same thing. When atoms come together, based on our conversation, it should make sense to you that pretty much on the outside of the atom are valence electrons. So as one atom sort of comes in contact with another atom, it is really those valence electrons that come in contact with each other first. And they are really the ones that are involved in bonding. And it's only the valence electrons, for a lot of reasons, as we just talked about in terms of those periodic trends. They're not held as tightly. They're easily removed and things of that nature. Also, they are places where some nonmetals have openings to accept more electrons in. So this is where really all bonding comes into play. Regardless of the type of bonding, ionic bonding or covalent bonding that's going on, as we talked about, as sort of the overwhelming principle of what is occurring is a very simple idea of everybody's trying to hit that noble gas electron configuration. So that is essentially really the goal of all bonding. So when we use Lewis dot symbols, we use the symbol and we use a dot to represent each of the valence electrons that a particular atom has. It should be important to remember that although in the Lewis dot symbols, we really just use dots to represent the valence electrons, but each of these atoms obviously have those other core electrons that are still there. They're just not obviously involved in bonding. So when we look at something like, say, sodium, which is 1s2, 2s2, 2p6, 3s1, this right here, again, is its valence electron. Once again, these are its core electrons. And typically, Lewis symbols are pretty much the symbol and one dot to represent each valence electron. There's no real big rule except that pretty much you shouldn't go more than 2 per side, right? So a lot of times people will do kind of 1 on each side and then come back and fill it up. Does it really matter? It doesn't. As long as you typically don't go over 2 per side. Clearly, on the 4 sides, we end up with the magical number of 8, right? Which is the magic number of bonding. Also happens to be the number of valence electrons that our noble gases have. And again, the purpose of it. So if we look at sodium, we would do its sort of Lewis dot symbol like so. 1 dot to represent the valence electron. You could clearly write out the electron configuration for everybody to figure out its number of valence electrons, but that seems like it's going to take a very long time in a lot of cases. The number of valence electrons in an atom is basically equal to its group number. So here we have sodium, which is group number 1 on the periodic table, which means sodium has 1 valence electron. If we did our 1s2, 2s2, 2p5, which should be fluorine, these guys here would be the valence electrons, which is 7. And fluorine, again, is group number 7 on the periodic table. So a much quicker and faster way to figure out how many valence electrons there are simply just to go to the periodic table and find the group number, and that will give you your number of valence electrons. Again, you can write the electron configuration if you want to. In terms of the transition metal, as I might have mentioned earlier, most people will roll with 2 for the valence electrons. As we also talked about, I think when we were talking about ions being formed with the transition metals, they typically don't back up in a lot of cases to the noble gases. The good news is in most bonding situations, you're probably not going to run across too many transition metals sort of involved. So you don't have to worry too much about that. So most of the time, 2 is what we have going on there for our transition metals, but we really don't see it too much occur in bonding a lot. So here's some examples of some Lewis dot symbols I made one day when I was bored. I should really get a hobby, I suppose. But we can see here that everybody in group 1 has 1, 2, 3, 4, 5, 6, 7, and 8. Why does helium only have 2 valence electrons? That is the correct answer. Helium only has 2 electrons, so even though it's in part of group 8, it cannot have 8 valence electrons because it maxes out at 2. So helium only has 2 valence electrons. Everybody else in group 8 obviously has 8 valence electrons. Also, why, as we will talk about, when hydrogen makes a bond, it pretty much just needs to go to helium. That is why hydrogen should only have 2 electrons in bonding, because it gets it to helium, which is the next noble gas past it, and that's perfectly fine for it. Everybody else past helium obviously needs to get to 8, because then you're at neon and below in terms of the noble gases to get themselves to 8. So the 2 types of bonding that we're really going to talk about in this chapter here is ionic bonding and covalent bonding. So a reminder that ionic bonding is always going to be really between these 2 things, a metal and a non-metal. And what's always going to happen in this situation, because of those periodic trends we just talked about, the non-metal is pretty much going to go, I would like your electrons. The metal's going to go, I don't really care, go for it. And the metal is going to give away those electrons over to the non-metal. This is again where the creation of ions happen. We get a cation from our metal, which is positively charged. We get an anion from our non-metal, which is negatively charged. And what holds that together, once again, is actually the electrostatic attraction. There's absolutely no sharing of electrons that are occurring when you make an ionic bond. So you have a complete transfer of electrons that occur in that particular situation. And that is different than, as we will talk about here in this chapter, a covalent bond. A covalent bond is always pretty much between 2 nonmetals. And as we talked about, based on our periodic trends, because nonmetals are pretty much hanging out in the exact location, the same location there on the periodic table, they both, once again, are pretty much going to want to hang on to their electrons and kind of take other people's electrons. So once again, in this situation, what we end up getting is some type of sharing of electrons that occur here. And as we'll talk about in this chapter, the sharing of electrons may be equal, or it may be unequal sharing of electrons that will occur. And that results in 2 different types of covalent bonds. But once again, always non-metal and non-metal, because of those periodic trends like ionization energy, electronegativity, electron affinity. The best that they will do with each other is share electrons. When we get guys together on opposite sort of sides of the periodic table, that is when we're going to get a complete transfer of electrons and an ionic bond going to occur. Bless you. In general, things with low ionization energy, as we talked about, will tend to form cations, because again, it doesn't take a lot of energy to remove the electrons, so they're able to become positively charged relatively easy. Things with high negative electron affinity means that they typically probably have gained electrons to get there, and they will form our anions. Any questions on that there? All right. So general rule tells us, again, cations there, group 1 and 2, really are metals on the left side of the periodic table. Halogens, oxygen, nitrogen are going to be our negatively charged ions. So let's take a look at an example of ionic bonding here. So let's say we took lithium fluoride. If we take lithium, which is 1s2, 2s1, electron configuration, and we take fluorine, which is 1s2, 2s2, 2p5 in this case. Once again, lithium is group number 1. It has 1 valence electron, which would be this guy right there. And if we drew the Lewis dot symbol for it, we would have something that looks like this. Once again, 1s2, 2s1. Fluorine has its 7 valence electrons, which are these guys right there. And that means it should have 7 dots there with our 1s2, 2s2, 2p5. So because we have our metal and our non-metal here together, our metal is going to go ahead. You could have my electron. It's going to transfer its electron over to the fluorine. When it does that, at this point, my lithium now will lose an electron and gain a positive charge in this case. My fluorine will pick up that electron. And because it picked up an electron, we'll have a negative charge in this particular case. And this would represent the ionic bond between lithium and fluorine. Couple things to note, they both have charges. And you should include the charges when you draw Lewis symbols for ionic bonding, because that indicates there's absolutely no sharing of electrons happening here. Usually in minimum, like I did up there, somebody will put a bracket around one of them, like the negatively charged ion. But you definitely should have the charges included here. So let's see what happened here on the other side when we formed this ionic bond. When we formed this ionic bond, pretty much lithium just gave away this electron, which means lithium with a +1 charge ends up with an electron configuration of 1s2. Who on the periodic table is 1s2? It is helium, and that would be a noble gas. So lithium has now achieved the same electron configuration as helium. They're isoelectronic with each other, as we talked about the other day. They have the same electron configuration. That one electron, once again, is going to migrate over here to fluorine, where it has room for it in its p subshell, right? Because p subshell could hold 6 electrons. At this point, it's only got 5. So we can pick it up right there. And when it does, it ends up with a configuration of 1s2, 2s2, 2p6. That is 10 electrons. Who is 10 electrons on the periodic table? That is neon. So again, this is the basis of bonding. In this case, the metal lays up its electron, gives away its electron. It's able to move back on the periodic table to the noble gas that comes right before it and achieve the same noble gas electron configuration, which makes it really stable. The fluorine picks up the electron and moves forward to the noble gas that comes after it and also achieves noble gas configuration. Everybody is happy in this particular case. Any questions on that there? A much maybe prettier example of that, but there we go. So once again, though, it is important to remember that what we are seeing here is a bond that is being held together by really the opposites attract. So the positively charged ion and the negatively charged ion are electrostatically attracted to each other. Once again, there's absolutely positively no sharing of electrons happening in this ionic bond. Let's take a look at another example. Let's take a look at calcium oxide. That's obviously calcium and oxygen together. So calcium here got a little electron configuration, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Oxygen has got an electron configuration of 1s2, 2s2, 2p4, I believe. Now, in terms of calcium, the two valence electrons it has are those two right there. It is from group number 2 on the periodic table, which is a much easier way to figure that out. So we would draw our calcium here with its two valence electrons. Perhaps we'll shorten its electron configuration as argon 4s2 in this particular case. Our oxygen there, which is group number 6, that is these 6 valence electrons right there. So again, we could look at the group number to help us out there. We'll do our 6 electrons like so. And again, our 1s2, 2s2, 2p4. Once again, here we do have a metal and a non-metal together. So our metal is going to give away an electron over to oxygen. If my calcium just laid up at that point and gave away 1 electron, would it be happy? It would not, because it pretty much would just back up to potassium, which is an alkali metal, but not much of a noble gas. Yeah. So in this case, calcium is going to want to give up both electrons to allow it to get back to its noble gas configuration. So the second electron here will also come over to our oxygen. The result of that at that point is our calcium will now gain a +2 charge, as it has lost 2 electrons in this case. Our oxygen there will then pick up those 2 electrons, and that's going to fill this guy out. It also, because it picked up a couple of electrons there, will end up with a -2 charge. Once again, you do need to include the charges. And there again is absolutely no sharing of electrons happening in this case. If we look at, again, the effect on the electron configuration, our 2 electrons from calcium going to be lost, going to yield us argon's electron configuration, going to leave it with 18. The 2 electrons will then end up over there in the space of the p subshell, which is room for it. And that will fill out the p subshell to 1s2, 2s2, 2p6, which once again is 10, our neon's configuration. So again, in this situation, we have both of the elements being able to achieve noble gas configuration, in this case by losing electrons and gaining electrons. And we see the same pattern as we saw previously. Metals are backing up to the noble gas, and non-metals are going forward as they gain electrons to the next noble gas. Any questions on that there? All right. So what happens though if maybe we put together a couple of things that we just saw, which is calcium and fluorine? So why don't we put those guys together? Here, I'm gonna find a spot to the right here. That'll work. Let's say we put together calcium fluoride, right? So once again, we have our calcium, which is argon 4s2. We have our fluorine, which is 1s2, 2s2, 2p5. Once again, our calcium having its 2 valence electrons. Our fluorine here, which has its 7 valence electrons. So now in this case, when we put these guys together, our calcium is going to give away its electron here to the fluorine. Now we kind of run into a little of a situation. Can the fluorine take any more electrons at this point? That fluorine is now filled, right? It cannot take any more electrons. And that's a problem for calcium because, as we just talked about a second ago, if it just lays up its 1 electron, it's at potassium, right? It needs to get rid of its second electron. So in this case, we would actually need one more fluorine to help us out in this situation. That second fluorine would provide room for that second electron to go. And in this case, we will end up with our calcium that was able to get rid of both electrons, one to each fluorine, resulting in it achieving the argon configuration. The first fluorine will pick up just one electron, which means it will actually pick up just a -1 charge, which is what fluoride makes. The second fluorine will also pick up just one electron and will also yield a -1 charge. -1 and -1 equals -2. That balances out the +2. Perhaps you remember, and we'll talk about it again, whenever you write a formula for an ionic compound, you always need to make sure what happens with the charges. They always need to balance out to 0 in the simplest way possible, which means the correct formula here is CaF2. The real reason we do that is actually for bonding, because if you balance out the charge in the simplest way possible, what you have just done is allow all those elements to reach noble gas configuration. So that's really the reason why when they tell you in nomenclature, balance out your charges to 0, that's really the purpose of why you do that. Question? So when we write formulas on the bottom here, you're talking? Yeah. So when we write formulas for compounds, we always indicate how many of those elements bottom right. So it's always a subscript, yeah, never a superscript. Other questions? Superscript is only the charge, yeah, if it had a charge, yeah. So when we do write formulas, obviously we'll talk about with naming as well. When we do write formulas for ionic compounds, you never write a charge, because the idea there is you're going to balance it out to 0. But it actually is made up of, as we can see here with our Lewis structures, our symbols, it is made up of 3 things that actually do have charges. So if you write a individual ions formula, you would include the charge. Why does the +2 and -2 go away? Basically will balance out it will actually balance out to 0. So that's the answer. And the reason, well, the common sense would say it would balance out to 0, right? If we take +2 and -2. But the real reason why we balance it out to 0 is really for what we just did here with the bonding. The real reason behind that is when you balance it out to 0 in that simplest way, that's allowing each of these 3 elements here to actually get to the noble gas configuration. So that's the real reason why we balance it out to 0. When we teach nomenclature, sometimes just go make sure it's equals 0. And the purpose of that is so that you get the right combination of each of those elements to get everybody to that stable situation of a bond that would happen in an ionic compound. And to that point, I'll get right to you. To that point, if we look at both of the fluorines, each fluorine picks up 1 electron here, and that gives each fluorine 1s2, 2s2, 2p6, or each of the fluorines actually reach neons configuration. So in this case, both of the individual fluoride ions have reached neons configuration. The calcium ion has reached argon's configuration. And they do that basically by balancing charges, but really what they're doing is completing everybody's octet and getting everybody to 8 electrons. Your question, or? Yeah. Yeah, so the good news is in most chemistry classes that you take, you won't do anything with bonding with the transition metals. And it's really because of that. They typically don't achieve noble gas configuration because of those d orbitals and stuff like that. But to answer your question, most people would say that those transition metals would have those 2 electrons being their valence electrons, because they technically are the highest. But as we saw when we were talking about electron configuration, we do dip into the Ds if necessary, right, to kind of get to the proper charge and stuff like that. So I've seen people say 2, and I've also seen people say, well, depending on which one, it could have anywhere up to like 12, because technically you could go into the d orbitals afterwards as well. But most people would say 2. Good news is we won't come across any of those guys in bonding. Yeah. Other questions? Yeah, how did I know I needed 2 fluorines? Yeah, it's exactly that. 2 reasons. When that fluorine accepted the first electron, pretty much it was filled at 8. So 8's pretty much the octet rule, right? Is the maximum you could get there, except for hydrogen, should only have 2. That's good for the fluorine, because that would allow that one fluorine to reach the noble gas configuration. It's not so good for the calcium, because it only allowed it to get back to potassium. So that's why we needed pretty much one more fluorine to offload the second electron in that particular case. Other questions on that? Okay, so this is again how we represent ionic bonding using Lewis dot symbols. You need to be able to draw these things, yes, with the electrons going in the right place. What you end up with on the other side, this should have charges, maybe some boxes around them, and understand obviously what happens in terms of the electron configuration for everybody as we go through it. Any questions on any of that there? Once again, that's all held together. All 3 of those guys are held together by positive, negative attraction. So again, absolutely no sharing of electrons happening here with the calcium and the 2 fluorides. All right. So that was ionic bonding. So let's talk a little bit about covalent bonding and some rogue electrons happening here. That totally missed. There you go. All right. So covalent bond, as I talked about before, is always going to be between 2 nonmetals. And again, because of those periodic trends, we're going to actually have sharing of electrons here. So very different than what we have in an ionic bond. Here we're going to have sharing of electrons. And as we will talk about here, the sharing will be sort of equal in certain cases, and it will be unequal in other cases. Gilbert Lewis suggested a role of electrons in bonding, hence why we call it Lewis structures after this guy. He basically thought, I'm just going to redraw this mess. I think it's okay on your handout, but we basically have 2 hydrogens here. So clearly in this case, since they are both hydrogen, they have the exact same periodic trends because they're the same element, which means what they're going to do in this case is actually going to share those electrons between them. Again, because hydrogen is a nonmetal, even though it's hanging out over there with the metals. And what's going to happen is we are going to create a bond between the 2 hydrogens where those electrons are actually going to be shared in this case. And when we count up the electrons in this situation, the 2 electrons there count for the hydrogen on the right. The 2 electrons count for the hydrogen there on the left. And the result of that is, in this particular case, by actually sharing electrons rather than transferring electrons, we end up with hydrogen having 2 electrons on the left, if you will, and also 2 electrons on the right. And as we talked about before, that is pretty much perfect for hydrogen, because if we go to the next element on the periodic table, it is helium, which is 2, and that is all hydrogen should ever, one more time, ever have. Yes. So if you find yourself in the wee hours of the exam, I'm not sure why it's wee hours of the exam, but it might be, and you drew a line like this and you decided, I feel like it looks more scientific-y like that, you should also draw a couple of lines like that, couple of electrons like that, and an upside down phase like that. Never, nor my other favorite, no double bonding the hydrogen, no triple bonding the hydrogen, or my personal favorite I've seen over the years, the triple bond of the hydrogen, and I'm not sure, so let's lay up some dots as well, just to be safe, right? Now we filled in every option possible. No. It's like a double no phase right there, right? So hydrogen basically follows what is known as the duet rule. I know somebody will draw it. It's okay. So hydrogen does follow the duet rule. And that basically means, again, it really just needs to get to helium. Should only basically have one bond, which is a sharing of 2 electrons. That means we never find hydrogen in the center either, because if it's in the center, it's probably got more than one bond happening and more than 2 electrons. Hydrogen should always be on the outside, single bonded out. We could show the bonding here as obviously the dots like we see here. We also could obviously use a line to represent those electrons being shared. So one line represents obviously 2 dots or a pair of electrons that are being shared. That's basically a single bond, right? When we share basically one pair of electrons. So once again, a covalent bond is the sharing of electrons, and these electrons are obviously attracted to the nucleus of this guy, right? But they're also attracted to the nucleus of the other guy that's over there. So that's what kind of holds those electrons in between the 2 atoms, is that sort of mutual attraction to the nucleuses on either side, kind of locks everybody in, that, you know, they're not going to hopefully escape too much in that situation. Any questions? All right, I expect no bad hydrogen examples on anything. I'm going to say it's just all going to be hydrogen. I'm just going to tempt you to draw as many lines as possible. Yeah, so don't screw it up on purpose. In a covalent bond, again, as I said, they're basically going to be shared. They're attracted to each of the positively charged nucleus, and that's really what's going to hold those guys together. We take a look at another example, like a couple of fluorines here. We have fluorine that has 7 valence electrons. We have another fluorine with 7 valence electrons. Once again here, because they're both the same element and they're both nonmetals, obviously, we're going to get sharing that's going to occur here. And what we see is you can represent it one of 2 ways. You could use all dots if you like. You could use a combination of dots and lines. Usually the lines represent the electrons that are being shared, or a bond. But if we look at the fluorine on the left and count up all the electrons, it has 8 electrons, which gets it to the noble gas configuration. If we count up the electrons there on the right-hand side, it's also got an 8-pack right there with those 2 electrons being shared in the middle, and allows, again, both of the fluorines here to hit the magical number of 8 in this case. And again, really become a stable sort of bond that's happening here. Now, when we look at this, there's a few different types of electrons that we deal with when we draw a Lewis structure such as this. All these electrons here are not involved in any type of bond, and we know that because there's no other element written on the other side of the dots. And those are what are referred to as lone pairs, which I personally oftentimes call it. A lot of times now people call it non-bonding electrons. So non-bonding electrons, lone pairs are basically the same thing. They are the electrons that are not involved in bonds. Question or was it? Yeah. Yeah. Yeah, it would be incorrect in this particular example, but you can triple bond something and have 2 dots on the outside. That's okay. Yeah. And like nitrogen is an example of that. We'll look at it in just a second, but nitrogen is actually triple bonded, and you would have 2 dots on each of the outside atoms in that case. Nitrogen looks something like this. And to answer your question, you could lay up the dots here and here if you like. Some people will lay up the dots there and there. You know, either way is fine, as long as you have the dots in this case. No, and we'll talk about when we talk about drawing after Lewis structures as to why this ends up being triple bonded, and we'll talk about the proper way to draw Lewis structures in this chapter a little bit later on. But there is a reason why you should end up with a triple bond in this case, and not just dots randomly drawn out. So as we'll talk about in this chapter later on, there's 2 common mistakes that people sometimes want to make. And one mistake is not to point you out or anything like that, but one mistake is something like what you described, where, you know, we kind of just lay a single bond and put dots everywhere. The other very common mistake that people make when they draw Lewis structures is they like to like triple bond and like double bond right out of the gate and start drawing bonds to everything. And there's really sort of an order at which you should sort of follow as you draw Lewis structures that will lead you to probably a pretty good structure when it's all said and done. And we're going to go through those steps a little bit later on in this chapter. Other questions on that? So to answer your question, there's also a reason why you shouldn't triple bond this guy, and then we'll get to that as well. So those non-bonding electrons are the electrons that obviously are not participating in any type of bond. Like I said, I personally, well, you probably say lone pairs most of the time. So when I say lone pairs, it's non-bonding electrons. Most book go with non-bonding electrons these days. The other bonds, electrons here are actually the ones that are involved in a bond, and they also have a very fancy name. They are what are referred to as bonding electrons, basically. So bonding electrons are obviously the electrons that are involved in a bond, and it is the bonding electrons that are typically drawn with lines. So if you want to draw the bonding electrons with lines, you can. Once again, a single line there represents two electrons or a pair of electrons, which is a single bond. As we'll see, two lines is two pairs of electrons, is a double bond. And obviously the triple bond, like a nitrogen there, would be three lines, which would represent basically six total electrons, are three pairs of electrons that occur. No, by triple bond, you should probably be good in most situations. Yeah. No 400 bonds, the one thing. A Lewis structure is again a representation using Lewis dot symbols, where we show obviously lines to show bonding, dots to show the non-bonding electron. You should 100% always show all those electrons. So sometimes other things that people commonly like to do is kind of leave off the non-bonding electrons. It's really important when you draw these pictures that you always show those guys. As I mentioned earlier, it is only the valence electrons that we see in the pictures, but they do have obviously more electrons, which are those core electrons. But because the valence electrons are only the ones that are involved in bonding, those are typically the only ones that we see. Here's what water looks like. And once again, we can see by sharing electrons with both hydrogens here, the water is able to, or the oxygen is able to achieve 8 valence electrons. Once again, each hydrogen, by sharing electrons, is able to achieve 2 electrons, which is exactly what it should have. And again, there's our fluorine example that we saw earlier. So that brings us obviously to the two rules that we sort of talked about, but officially here, let's talk about it. One is obviously the octet rule. Other than hydrogen, pretty much everybody will continue to lay up bonds until they get to 8, which to answer your earlier question is why they would lay up before they get to like a quadruple type bond or a penta type bond or something like that. Yeah, it is, but typically they wouldn't need to do that based on how electrons are placed in the atom, iron molecules, because the way we kind of place electrons, as we'll talk about, is outside in. So electrons get placed on the outside ones first and then the inside last, which means you would never usually have to get to that point. By sharing electrons, we continue to make bonds, and in some cases, to reach that 8, all you need is a single bond. And in some cases, like we just saw there with nitrogen, you need a triple bond. And in some cases, you do need a double bond to get everybody to 8. Again, our hydrogen is the exception there. It is sometimes referred to as the duet rule, which means that hydrogen only needs 2 electrons to be happy, gets itself to our good friend there, helium. So here's again some examples of single bonds and double bonds. Our single bond there, one line representing 2 electrons or one pair of electrons. Carbon dioxide actually has a couple of double bonds. So in the case of carbon dioxide, it actually does need to lay up some double bonds. And by doing so, the carbon is able to share electrons with both of the oxygens, which gives the carbon in the middle 8 valence electrons. Each of the oxygens on the outside there will also have 8 valence electrons by also sharing with the carbon. And in the case of nitrogen, for example, again, it is able to achieve basically the 8 valence electrons by, in this case, having to triple bond. That's basically ethyne there. The carbon in that case has to triple bond with itself or the other carbon. And by getting the 6 electrons being shared there, plus the 2 being shared on the outside there with the hydrogen, allows each of the carbons to get the 8. And once again, we see our hydrogen on the outside having only 2 electrons that are occurring. As I mentioned a second ago, also a super common problem. People just really love to like triple bond and double bond everything. And usually a good way to think about double bonds and triple bonds, especially when you start drawing Lewis structures for covalent compounds, is to think about double bonds and triple bonds as sort of fixing a situation where somebody does not reach the octet rule. So you kind of want to only kind of do those things, lay up a double bond or a triple bond to sort of fix a guy that does not meet the octet rule. If you could get somebody to sort of meet the octet rule with just a single bond, that's usually preferable in most cases, and you should do that. You shouldn't, again, just add extra bonds to make things look more chemistry-ish. Electronegativity, that's a word, look it up. Electronegativity, as we talked about earlier, is the ability, again, of an atom to bring electrons towards itself. So electronegativity is that ability to bring electrons towards itself. As we talked about with our periodic trend, we do see it increase as we go up to the right and decrease as we go down, with our guy fluorine being the most electronegative atom. It is actually electronegativity that is the overwhelming issue as to whether or not, when you put 2 atoms together, will the electrons be shared equally or will they be shared unequally? So electronegativity's real sort of value is in the idea of how those electrons are going to be shared. When we look at a bond between our hydrogens, for example, obviously they're both hydrogen, they're both sharing those electrons in the middle. And because they're both hydrogen, we would expect basically those electrons to be attracted to the hydrogen to the left and the hydrogen to the right pretty much equally to one another. They're going to pull those electrons equally, kind of like 2 people. They're exactly the same pulling on a rope, right? The rope's going to probably not go anywhere, right? If you pull them together, it will not pull one way or the other. And we would expect that these electrons be shared equally. And this type of bond where the electrons are actually shared equally are what are referred to as a nonpolar covalent bond. Most people will just simplify it and call it a nonpolar bond. So a nonpolar bond is essentially a bond where we have equal sharing of electrons between 2 atoms. 100% of the time always occurs when you have actually the same element involved in the bond. You will always get the same basically electron pull. We see that with the F2 that we saw earlier. Those guys as well, we would expect basically each of those fluorines to pull those electrons that are being shared equally to the right and to the left. And that's also what sort of locks them into place. So we're going to have a nice equal sharing of electrons. That would be considered a nonpolar bond between those 2. And it's that electronegativity aspect of it that is doing that. Each of the fluorine has a certain pull for those electrons. And in this case, the pull is going to be the same. Now, what happens when we sort of swap out perhaps a fluorine for another element like hydrogen? We no longer have basically this same element on each side. And as we know from our conversation about electronegativity between hydrogen and fluorine, which one is more electronegative? It is the fluorine, which means when fluorine is attached to hydrogen, what's going to happen is all the electrons are pretty much going to decide we would like to come over towards the fluorine side of the bond, and not a lot of them are going to hang out over there towards the hydrogen side. The result of this is a lot of green marks on the board, but other than that, the result of this is we are no longer going to have equal sharing of electrons. We will have some unequal sharing of electrons that's going to happen here. Also, a result of that is if the electrons are heading towards the fluorine side, will the fluorine side be more positive or more negative? It will become more negative. So what happens on the fluorine side in this bond is it creates a partially negative charge. And on the hydrogen side, it creates a partially positive charge. Those are delta symbols, partially positive, partially negative charge, which can be represented by those symbols. We oftentimes will also represent it with a line where it points to the side that is more electronegative. So it always points to the side that's more electronegative, and the side that makes like a positive sign on the back end of the arrow is to the sign that is less electronegative. When we end up with unequal sharing of electrons in this case, this is what is known as a polar covalent. Polar covalent bond, and it is oftentimes referred to as a polar bond. And we have unequal sharing of electrons. Why is these guys only partially positive or partially negatively charged? Yes. Well, part of that's right is because it is still being shared. Yeah. So because this is a covalent bond, it is still being shared. It has not completely transferred from one to the other like we see in an ionic bond. In an ionic bond, the electrons completely transfer from one to the other, creating a positive charge and a negative charge, fully charged, because the electrons have fully transferred. Although these are not being shared equally, the key point here is they are still being shared. So they're still hanging on. So we don't get that full transfer of the charge. We create sort of a partially positive charge and partially negative charge that occurs on the fluorine. Any questions on that there? All right. So once again, this is a very common sort of way that the polar bonds are represented. This is what is sometimes referred to as a dipole arrow. And again, always points to the more electronegative side. And this side is always to the least or less electronegative side. We use that sort of arrow a lot in bonding to represent polar bonds. We never use it to represent nonpolar bonds because there is equal sharing of electrons. And a nonpolar bond is essentially like a neutral bond. There's no side that's more positive. There's no side that's more negative because of that equal sharing of electrons. Any questions on that there? So to summarize sort of the three types of bonding we talked about here, on one side of the spectrum, we sort of have an ionic bond, which once again is always between a metal and a non-metal. And once, as I mentioned, we have a complete transfer of electrons. The result of that is we're going to gain full charges here. We're going to gain a cation that has a positive charge and an anion, which is negatively charged. Once again, no sharing of electrons. The positive, negative electrostatic attraction basically holding that together. On the other end of the extreme, we have a nonpolar bond, which is covalent, always between two nonmetals, where we have equal sharing of electrons, like our F2 example, our H2 example. And we have nice equal sharing of electrons where there really is no side that's more positive, no side that's more negative. And sort of in the middle of those two, we have a polar covalent bond. Also between two nonmetals. Also unequal sharing in this case, but we still have sharing happening. An example obviously would be our HF, where one side is going to become more positive because the electrons are basically vacationing on the other side, which then becomes more partially negative. Once again, this side are both covalent bonds. And on the left-hand side there is our ionic bond. Any questions on the differences between the different types of bonding? Okay. We'll lay it up there for today.